Formal methods. Formal methods kind of exist to answer the question, does a system, probably a software system, do what it's intended to do? And more specifically, does it obey a specification that's in a sort of formal, maybe a compilable language? So how do we know? Mathematical proof, actually. So you can, model checking kind of refers to the process of enumerating all the states that a system could be in and checking in each state that it obeys certain properties. Automated theorem proving doesn't do sort of that sort of process, but rather generates a proof that a system is correct kind of iteratively and possibly even with some, it says automated, but even with some human input. Okay, further question, given a specification formally written, how could we actually create code implementing that specification? That's called synthesis or program synthesis. All right. So traditional use cases, circuit design. It's really hard to make sure that your circuit comes out exactly right, especially you can reason about maybe a simple unoptimized circuit, but then if you optimize that circuit, how do you know that it does the same thing as the one you could reason on? Mission critical software, say embedded systems of different types, even medical devices. That's an interesting use, like pacemakers should really all be formally verified. And in fact, pacemakers might have a few enough states that you could model check them. I've heard the numbers like 12,000. UAV piloting software, that's a bit of a joke, but they really do formally verify that stuff. And yet, Amazon Web Services, that really needs to behave properly all the time because of the load the system's under and sort of what it would do to our economy if Amazon Web Services had incorrect behavior. So newer use cases. Educational software, actually. You can use formal methods to test if someone's code that they submitted is correct. And you can even start maybe moving into things like math, where you just check the proof. That's pretty easy. But that's an emerging use case. Security vulnerabilities. So you can create a formal model of maybe a cryptographic system. I read a paper concerning OAuth. They spec'd, some nice model of OAuth that's maybe not completely accurate, but accurate enough. And they found old holes in it, and they found new holes in it just by doing a sort of model checking method where you just check that certain security properties hold in every state, and in fact they found that they did not hold in every state. And I think it's very important for cryptocurrency, for one, clients. The value of the cryptocurrency itself is determined by the correct functioning of a piece of software. So if that software doesn't function, the value could pretty easily fall to zero. And as we've just heard, smart contracts as well. So you can do some network modeling with these things too. That's starting to appear as a use case. Won't go too much into that. And yes, there was a question mark before the presentation that Elaine just gave. But yeah, verifying smart contracts for correctness. All right. So in principle, verification is hard because the easiest verification problem is NP-hard. That's just satisfiability. Model checking requires exhaustively searching some potentially enormous state space, or if you're modeling time, say, possibly infinite state space. How can you do that? But in practice, so this is a slide there are two slides from a class I'm taking at Berkeley with Sanjit Seshia. So the slide on the left side of the screen is on the same hardware, algorithmic improvements in SAT solvers. And a little over a decade, you can't even see the last bar because there was a 1,000-fold algorithmic improvement in satisfiability. So much so that satisfiability is viewed as an easy problem, even though it's NP-hard. In the other case, the spin model checker, so the graph is talking about memory, and kind of you can see in maybe 1987 the problem crossed over from infeasible to feasible because the amount of memory required to check all the states of a certain system, it's actually a telephone switch of some kind, probably not an enormous number of states, fell just due to algorithmic improvements. And we'll see how long that trend goes, but it's actually very much possible to do formal methods in production these days. So last slide, main bottleneck, probably developer effort and expertise. You have to really think hard about the formal spec. To a business guy, it seems like that'll really lengthen the develop cycle. In the long run, it might not. If you thought about the formal spec earlier on, it's possible that the software will be much more maintainable and scalable. But we'll see. Anyway, thank you.
I just want to give a quick example. Like I talked about this ideal world style programming where the user can focus on creating the functionality without having to worry about the cryptography. So I'll give a very narrow scoped example about how this is, what this looks like, but the kind of things that we want to do is much, much broader than this example. Okay, so in Bitcoin, here it is. When Bitcoin came out, and probably a lot of you know this problem, the Bitcoin blockchain is essentially a big authenticated data structure storing all the past transactions such that you can, the authenticated data structure part gives you some kind of verifiability of this data structure. There's one flaw with the design in the sense that the new miners, when they download the transaction history, they have to start from square zero and compute the current ledger. In some sense, you can think of every transaction as being an operation and the ledger being the final state. Okay, so doing this operation for new miners is expensive. It takes linear time in the size of the blockchain. Okay. There's an obvious solution, of course, to this problem in the sense that we can redesign the blockchain to embed the ledger in itself as well, which means you also have to create an authenticated data structure for the ledger as well. Okay, so why is this not done? And now we realize this is better. Why don't we incorporate it into Bitcoin? There are some possible answers to these questions. Here's what I think. Why wasn't this done in the first place? Thinking about the functionality and thinking about the crypto at the same time is hard. Okay, so in this case, like if the programmer has to do both at the same time, it's easy to kind of, not do the best job. Okay, why didn't we modify Bitcoin to incorporate this? Software updates for cryptocurrency is an expensive process. If you want to do an update, you require community agreement. And how do we even know that the new implementation is actually secure, right? What if it is buggy? This can be really bad. So we came up with this programming language called Lambda Auth. Okay, the idea is that programs written in Lambda Auth can be automatically compiled into an authenticated version while ensuring formal security. Okay, I won't talk too much about the programming language. This is also might be relevant to Ethereum because Ethereum has this Merkle-Patricia trie, and the idea is you want to create like a history-independent data structure such that the end state is independent of the order of the operations. So if you had something like Lambda Auth, the programmer could just focus on programming the programming the Merkle-Patricia trie without having to worry about the crypto at all because the crypto will be automatically generated. Okay, so essentially, I just want to say this is not just about fixing the cryptocurrency, the Bitcoin blockchain, and this is not just about the Merkle-Patricia trie. Essentially, take this idea and think about it in a much broader context. You want, let's say, every smart contract programmer to be able to just focus on, I want to create this smart contract such that it satisfies these security properties. And the developer in this case doesn't have to worry about how to instantiate the cryptography to achieve these security properties. Okay, so yeah, thanks.
Yeah, I presume you hadn't heard of Solidity when you did the class with Serpent? There's a language that we're developing in Berlin called Solidity, which is... Okay, no, that's okay. So I'm going to show you a little bit of this language. Very simple example, but just to give you an idea of probably some of the concepts that you were actually talking about. The difficulty of programming things in Ethereum hadn't missed my attention, and this came from sort of trying to make a few contracts and realizing that actually we don't have a language or that I was aware of at least, that was really well designed for writing contracts, for writing these sort of autonomous objects on the blockchain. So Solidity is a language that evolved from a bunch of requirements and nice to haves that I found while actually trying to do some of this stuff. Here's an example of a really simple contract. This is a coin, right? It's a coin contract. Or you might also call it like a currency. You might call it a check clearing system, whatever. The idea is that the contract is an autonomous object. It sits on the blockchain, and people can interact with it. It actually only has one way that you can interact with it, really, and that's this function called send. And what that does is it just person A, who is actually interacting with the contract, so they're authenticated. We know that they are actually sending this instruction. Want to send some value to an address. So this is based roughly around the JavaScript syntax for those of you who can program. The coin's entirely pre-mined, so in its initializer there, at the top, we give the person who creates it a whole bunch of money, and the send function is very simple. It just adds value to the balance of the destination, and it removes the value from the balance of the sender. So I guess hands up if you can understand roughly what this is trying to do. Yeah. Most people, good. Okay, so there's a notion that you can get the balance as well, and from your talk, Elaine, you were mentioning how difficult it was to manage the state. Having to use these numeric pigeonholes to place your state. So this is something that we've. Yeah. So this is something that we fixed very early on in Solidity with the notion of mapping. So mappings allow you to say, right, well, I want to take an address and turn it into a unit, and I want to store what these integers are for every address. So it's a very simple sort of mathematical notion of the word of mapping. And what we're doing is we're saying, right, well, we want to make a mapping. We're going to use the storage of the contract, and this particular mapping is called balance, and it's public because people outside the contract can sort of ask what someone else's balance is. And hands up if you can see a problem with this contract. 2, 3, 4. Not many. Okay. So what we're going to do is we're going to introduce a condition, right? This condition is called an invariant. And this is a formal way of stating that this contract has a property. So what we've done so far is state the process of the contract. These are the steps that the contract must do to execute. But processes are very hard to reason about. They're so hard to reason about, most of the people in the room couldn't understand what was the problem, and I'll show you the problem. So what we're going to do is we'll introduce a property, right? And this property is something that never changes, hence the word invariant. Roughly speaking, what it's going to do is going to map the balance with the value of operator. What it's going to do is effectively turn all the balances into their integers, so the amounts of value that's contained in every account, rather than the address of the account. We're not interested in the address, we're only interested in the value that's stored at the address. And we're going to reduce all of this big long list of balances of all the accounts using the plus operation starting at 0. So what this means is English, is we're going to add all of the balances together, okay? But we need to state this in a formal way. Formal proofing. And we want to say our invariant is that the sum of all of these balances will equal that same number that it was in the beginning. Okay? Now it's trivial to see that at the beginning that will hold true. Yeah, because in the beginning there's only one account that isn't 0, and it's that number. But as the contract changes state through people transacting with it, we want to be sure that this property remains true. So the idea is, of formal proofing, that we can put this through a compiler, and the compiler can read this, and it can understand that actually, hold on a minute, when this line executes, we have an unbounded value, and what this means is that this property may break if someone attempts to transact with this contract using some specific inputs. And that's very important, because without that, many of you would have missed that, and if you'd have wanted to interact with this contract, you'd have potentially lost a lot of money, or other people would have gained money on you, which is almost the same thing. So what we're going to do is going to add this additional restriction. So this is a way of again specifying a property. We might also have added just a conditional, like an if statement, that checked that this was true as well. But this is a slightly nicer way of doing it because it introduces property rather than process. And all this restrict statement means is this function can only execute if the balance of the sender is at least the amount of money that they want to send. Yep. And with that there, of course, it compiles fine. Okay, that's basically all I want to say. I guess the rest of the conversation we can between us.
Hi, I'm Anthony DeFranco. I'm actually working on a programming language that grew out of some potential smart contracts applications at a company called Credibles that I was working at. We were looking at a case where small business owners would sit down with their lawyer and their accountant and essentially do their own debt financing in the same way that something like Coinbase lets you do your own equity financing, where they would craft a promise to deliver something at a future time and then have a market that would make that liquid. So this is people who are not necessarily spending most of their time programming, creating programs that have to have a very high bar for correctness on them. So that was the impetus for me to start looking at how to represent these contracts in a way that they could be automatically verified, and not just Boolean properties of them be verified, but also so that you could incorporate probabilistic information or other forms of uncertain information into them, so that you could see what their expected value might be over time in different scenarios, or best case, worst case, expected case, so on. So that took me in the direction of doing information propagation networks, which is kind of a generalization of constraint solving, which is itself an approach that was originally used for, or came out of the logic programming research. And in order to make that fast, it ended up implicating research from not just programming languages, but information theory, operations research, a little theoretical neuroscience, oddly enough. And that project is right on the cusp of design and implementation right now. One of the things I wanted to mention is that it can do at least as much as a dependently typed programming language can do. So these arbitrary properties that you want to assure using the type system, I think you both mentioned that, but Elaine especially, that's part of the paradigm that we're staking out. So sadly, I don't have too much to show, it not having been implemented yet, but I definitely look forward to more discussions about how it might be used and to fill in the crypto side of things, because I've been much more on the programming languages research side of things. So looking forward to putting these two halves together.
Any questions?
So, your restriction, doesn't the programmer still have the problem of having to figure out all these restrictions, which is really just correct me if I'm wrong, but it's just it's formalising problem, but it's not helping solve the problem as well. So you still have to be aware of all of these things, and most people in the room, including myself, miss if we could overspend there, then we're still going to miss that.
So then the idea is that before you put it through the compiler, before you even write the contract, you pre-specify what these properties are. So, for instance, this contract, the property is that it's pre-mined, and that the amount of total equity in the system will remain constant throughout its lifetime. And that's that property that we put, that's the invariant. Now, you're right, I didn't have the restrict originally. It may be possible for the compiler to analyze the program and basically suggest, hey, you know, did you miss this? Just through some heuristic matching. But the most important thing is that the compiler warns you that that invariant does not hold, because it's the programmer still has to do their job, right? But it's important that also as somewhat as a third party that comes along, it's important that you can put the same program through the compiler and see that those invariants do indeed hold, because it may be that the programmer's trying to get one over you. They put the invariant in, but they don't put the restrict in.
So what's the mechanism you're using to check those, by the way?
We're not checking them yet, but it's on the to-do.
Okay. Do you have one in mind?
I think this is something that we'll probably talk about in this conference.
Is there sort of an alternative way, which is it's checking happens at runtime? So, for example, the uint anyways would probably you try to throw an exception when you try to take it in as zero. But you've got that declaration that the invariant the balance has to equal. Is it necessary to add the restriction clause?
So it's important to remember that the invariants are not part of the process. They're there to inform the compiler about why this, whether this contract is correct or not. So they're a way of us or the specifier, maybe not the programmer. The idea really is with formal specification that you put the specification up front before you even lift a finger in terms of implementation.
So it's not a dynamic. There's no dynamic.
So one thing here is that, you know, theoretically you could write in Serpents or Solidity or whatever, something like if this particular invariant doesn't hold, then throw an error, and the way that the errors work in Ethereum is that all the computation gets reverted. So that's possible. But the thing is that with this particular invariant, the time that it takes in order to evaluate it dynamically is basically all of that, right? Because if you have 20,000 balances in this thing, then it takes 20,000 steps, and you really don't want to do that when you have 20,000 users. So that's basically why it makes sense to kind of use separate logic to evaluate each of these.
Okay. Yeah, you still have racing conditions, locking, there's like so many issues here, right? So if I just add that to that, it's very difficult.
Right, so a lot of those conditions, a lot of those problems are resolved just because we have the way our VM design, sort of everything is synchronous. Although, you know, you might have conditions where A calls B calls A, but like generally the way this stuff should work is that every contract execution has its own sort of internal state, and then each individual execution round's internal state is sort of independent of everything else, of every other instance of internal state, and then sort of commits are done separately. So it's in some ways less of a problem, but in some ways probably is.
You have this really fun statement there that a contract can be kind of separated from the crypto. And I confess that I didn't follow all that. Could you kind of restate that again?
I mean, think about one way to think about it is think about that authenticated data structure example, right? So Ethereum, let's say, has this Merkle-Patricia trie in the design. So would it would be really nice if the programmer just basically programs the data structure itself, and not having to worry about how to do the Merkle hashes. So what I mean for smart contracts is along in similar veins. So let's say go back to the example I talked about in the morning. Let's say we have a game and rock paper scissors. We send our inputs to the contract, and you wanted the experience for the programmer to say, I send this input to the contract, and the input is private until the moment when they're opened. So that's what the program has to write, and then the commitment, all of those can be automatically generated. So that's one example.
Is this so? In the morning there is lots of discussion about snarks, which I think to be fully usable might be for academic work. Does this actually require more academic work, or is it kind of completely usable now?
There are many interesting directions of research. One is kind of making snarks in general more efficient, or making it more efficient for specific classes of computation.
Well, I was actually talking about this particular application here.
Right. So another very interesting direction of research is try to design the programming support. So snarks are very powerful, but suppose, let's say now we want to take, let's say, Solidity or the Serpent language, and we want to introduce higher level programming constructs into the language such that, if the programmer writes, I want this secret input to be committed to the blockchain, I want that secret input to be committed to the blockchain, and later I want to show a proof that this secret output is, the result of computing this function on the secret input. So basically, you want to create programming constructs that enable this, and also make it user-friendly in a way such that the developer can understand what the security property is, and not having to worry about implementing the snark itself. And there's also a lot of opportunities, like in the compiler, you can do optimizations. And so if the programmer were to do this, he really needs to be a crypto expert. Like, he needs to know, for this class of functionality, this type of snark is more efficient than the other, right? But if you think about it, all of this is knowledge that we know. We can automate this.
Well, I guess that's the question. Is the verification that you talked about, is it actually super usable at present, or is actually, for example,
you mean in terms of efficiency or in terms of the programming support? There's basically almost no, you can, this could be a little bit exaggeration, but there's basically almost no programming support. There's a little bit that's being developed by the research community, but not along the lines that I talked about, like the ways that I envision to incorporate it into the Serpent or Solidity language. But in terms of efficiency, I would say general purpose snark is somewhat practical. The efficiency, of course, there's a lot of room for us to improve the efficiency for it to be maybe really, really, really practical. So it does, what I mean is it is practical in certain application domains. That is, like, if the prover's time, you don't have very strong requirements or constraints on the prover time. So the verification will be really fast, but right now the prover still takes some amount of time.
Yeah, I was actually, in the snark case, I was actually thinking about the initialization, but anyway, thank you for all that. Very good.
One more question on the scalability.
What do you think of Solidity now? And is Lambda auth compilable to EVM now? Like, what's the status of Lambda auth?
Lambda auth?
Who was the Solidity question? Yeah.
What I think of, I think it's a really cool idea, and I'm very interested to take a look at that. And I think with something like Solidity, maybe the next natural question to ask is, how do you automate the crypto protocol generation? And I think also for Solidity, there might be a lot of interesting programming language research on how to actually support richer predicates that you want to check, and how to do that in a formal manner. So for instance, the example that Gavin gave, for instance, maybe one of the most simple kinds of constraints, but you can really think about more complex constraints, like maybe those that involve probability. Let's say you are playing a game where a coin or a dice is rolled. So in these cases, you want to specify some fairness constraints that involves a probability distribution. So think about all these expressive constraints that people may want to express. Would be also very really exciting and interesting direction. Sorry, what is the question about Lambda auth? Lambda auth, we have an open source implementation, and it's kind of embedded in OCaml. And we have open source, so you can download it and go to my webpage or Andrew Miller's webpage, and there's a link, and you can download and play around with it. It's kind of like an independent project right now. It's not hooked up with any cryptocurrency.
So just concerning the cryptographic primitives, I'll say a quick, I'll plug Solidity a little bit. There's our multi-signature wallet implementation, as it stands, actually uses 2 cryptographic primitives. So the multi-sig bit is actually a cryptographic primitive. The wallet is actually just a transaction proxy that requires multiple signatures. So it's when I say, contract-oriented language is perhaps pushing it a bit. Really, it's just an object-oriented language with a few bits of idiomatic grammar and vocabulary. But because it's object-oriented, we do have the ability to inherit, what are effectively primitives, and so we can do this sort of stuff where we may want a sort of well-tried, well-tested, well-trusted piece of code to do things like rock paper scissors style commit reveal protocols, and that can actually just be sort of inherited right into the contract to guarantee the validity.
So is that currently supported in the current Solidity? Like, can you have these automatic generation of
It's in development, but there are we have that.